Okay, so we have a regular differential equation. We have a regular derivative in here. So what I'm going to do is start lifting things out here. So I have u is this expression, and I lift out a1y plus another constant. I'm going to call that a2. And v, I'm lifting out the v. I have that a1x plus yet another constant. So let's count the constants here. A1, A2, A3, so we have 3 constants. That should give you a hint of where we're headed here. So we're going to pop this into the original expressions for u and v because I picked up those functions of integration just now. And you could use different letters if you don't like this, but u1 of y, v1 of x, you could call them different things. So I just solved for these guys, so I'm going to pop it into here. So I have u as a function of x and y with a1 and a2 constants, and I have v as a function of x and y with a1 and a3 constants. So obviously these 3 constants are based on geometric boundary conditions because this is u and v, so I must deal with geometric boundary conditions, not stress boundary conditions. Very, very important. So let's go back to the original picture here. What's our problem here? It was a cantilever beam, remember, with a point load, and the boundary conditions are pretty straightforward here. At x equals L and at y equals 0, there's a little subtlety here. It's on the neutral axis. So at x equals L and y equals 0, the displacement u is equal to 0. At x equals L and y equals 0, the displacement v is equal to 0. So notice this extraordinary emphasis that I'm placing on it in this neutral axis. That started way back when, in the beginning of this lesson, that all of the information that we're talking about is limited solely to this principal centroidal neutral axis. It has nothing to do with the rest of the beam. And that's an interesting new insight that you didn't have as an undergrad. So we're talking about this point right here, not this point and not this point. So these are my 2 boundary conditions. Pretty straightforward. A2 pops out to 0. And we clearly need the 3rd boundary condition. And here's where it gets a little Star Trek-y. Okay, so watch me, and this is what you're going to do for homework. We need the 3rd boundary condition. Obviously, it's going to be slope. The slope is 0 here. But I'm going to define the slope 2 different ways. The first way is exactly the way you've done it as an undergrad, that the slope is dy or dv dx. So I showed it over here, dv dx, the rise over the run. That is the way you've always done slope, and we'll call that version 1. But the Star Trek-y part of this is, look at this, what's happening to the beam. The beam is penetrating this support here above the neutral axis, and the beam is pulling away from the support below the axis, and all of that's perfectly legal as long as the slope right here is 0, and the slope is defined as dv dx. And then for homework, I want you to do a second version of this where it's the run over the rise. Partial u, partial y. I hope somebody's head just exploded. Partial u, partial y is also the slope. And we're going to call that version 2 for your homework. Good luck.